Hi everyone. I wanted to share with you in this video a small tutorial on how to import a PDF, not a PDF file, excuse me, import an IFC file, create a graph for it as well as the geometry, and get all the semantic information from the IFC components into the graph nodes and into the graph geometries. I also, at the end of this video, I want to showcase a new method in the new version of topologicpy, which is, as of this video recording, 0.7.90 or 0.90, about creating what is called connected components. You can think of those as graph islands or subgraph islands from a larger graph. But we'll get to that in a second. Let me show you this Jupyter notebook and go through it. This Jupyter notebook, which is called Graph by IFC, I believe, is on my GitHub under notebooks, so you can find it there. But it's always a good idea to follow along and maybe type it in and see how it works for you. So I'm going to start sharing my screen. Let's share the whole screen. And let me hide these video panel and the floating meeting control so that you can see the whole screen. All right, so as we always say, the first 2 lines of code here, you don't need to run on your own computer simply because I'm using my development machine. So I need to add the path to topologicpy to my system. The second one, so I will run this one just to make sure I have it running. The second cell here is to import all the needed libraries. As you can see here, the ones that are grayed out were not used, so you can actually remove those if you don't need them, like this. And what I'm doing here on line 6 is I'm printing the version of topologicpy. Now, with the newer versions of topologicpy, and you will see it now soon once it prints, I did a really nice thing where it compares the version that you are running on your computer with the latest version on pyp.org. So it actually will go out in real time to pyp.org, grab that version number, and compare the two versions numbers to let you know whether you are behind or up to date on your topologicpy version. So let's run that. As you can see, it's going to take a little bit of time because it goes out to the web. And here it says the version that you are using, 0.7.90, is the latest version available on PyP, so you can make sure that you are using the latest version. Okay, so we did that. Now, in order to bring in now the IFC file, you have to specify the path to it. And in this case, you need to change this path to point to your own IFC file, as it says here. The IFC file that I have is under downloads, and it's called the IFC 2x3 duplex difference 1. You can choose your own IFC file and test it, see if it works. But this is going to be stored in a variable called IFC file path. So we run this one, and it's run. Okay. So the next step is to decide, out of this IFC file, what are you interested in importing? Obviously, IFC files can be very large and can have many different types of components. Sometimes for your own work, you don't want everything. You don't want perhaps doorknobs or toilet seats or beds or whatever it is, side tables. You just want simple things like an IFC space, for example, here. So in this, I decided to make a list of the things that I'm interested in. I called them include types. These are the types that are to be included. And what are they? An IFC space. Not all IFC files have an IFC space, but if they have it, I will import it. A slab, a roof, a wall standard case. I found out that actually there are two types of walls. So obviously you need to bring all kinds of walls into it. And doors and windows. So these are kind of like a simple set of elements or element types that I'm interested in. So I run this one, and now it is saved in something called include types. The next one is the actual cell that's doing the real work. So I'm saving something in graph 1, and I'm calling graph.byifc path. That is the call into the topologicpy API. What does it need? It needs the IFC file path, which I specified up here, excuse me, right there. It needs the include types. This could be left, it's optional. If you want to import everything, you just leave that out and it will import everything. So I basically included the include types here, which is the same variable name as you see here. And then transfer dictionaries equals true, meaning that I would like the nodes of the graph to have a dictionary that has all the IFC attributes that are coming in. So basically, every one of those elements, a space or a slab or a roof, will have a dictionary. And therefore, I transfer that and I represent that whole geometry with a single node or a single vertex. And I put the dictionary in there. Use internal vertex is basically the idea that, especially if you have a U-shaped geometry, the centroid of that U shape will be actually outside the solid, outside the geometry itself. That can lead to problems later on if you are trying to use a vertex to identify which object you're talking about. So in most cases, you would like that vertex to be inside the solid so that you can identify it later. Now, this is computationally more expensive. It will make the importing slower because it's trying to find a vertex that is guaranteed to be inside the solid, regardless of the shape of the solid. It could be convex, concave, whatever it is, it will find a vertex for you that is inside. But in this case, because I have a use for those vertices later on, I would like this to be set to true. The default that it is set to false, and it will just simply use the centroid of the object, which is a much quicker way to import those files. Now, the other one here, store BREP. BREP stands for boundary representation, and it is the kind of fundamental way we represent things in topologicpy using the open cascade BREP representation. I am asking it now, because I'm setting this to true, I'm asking it to store the geometry, the BREP of the geometry, inside the vertex. And topologicpy can do that. Basically, you can put it inside the dictionary of the vertex to say, here is the BREP representation. Basically, I convert it into a long string, a BREP string, and I store that string inside the dictionary of the vertex so that I can retrieve it later on. The last option is to remove coplanar faces. I'm using IFC OpenShell to import those IFC files. And also code, obviously, by Bruno Possel that provided me with the original code. Obviously, now it has been expanded quite a bit from the code that he provided. But the geometries that come through, if you do not remove coplanar faces, will be triangulated. So if you would like clean geometry, planar, not triangulated, you can set that to true. Again, there is a cost to this because it's a geometric operation where every geometry needs to be cleaned up. All right, so by the time this runs, we will get a topologic graph. Basically, a graph is nodes and edges, as you know. Great, so how do we extract the topologies from the vertices of the graph? So we're going to make an empty list for topologies. Square bracket means an empty list. And also, I found out this IFC file in particular, which somebody gave me, has some rogue vertices. These are vertices that have no topology associated with them, even though they are of type IFC space, slab, roof, wall, standard case, door, and window. Somehow, those rogue vertices did not have a BREP associated with them. I will investigate a little bit further when I have time why, but I decided to identify those and isolate them, remove them from the graph. That's why I'm making a list of rogue vertices. Okay, so now we have this graph. We go through the vertices of the graph. So for V in graph.vertices, graph 1. So I'm looping through every vertex in this graph. What do? I get its dictionary. So D is equal to topology.dictionary V. And then I get the BREP string from that dictionary. And I know that it stores it in a key called BREP. So dictionary.value at key, the dictionary is called D, and the key is called BREP. It will give me the value at that key. That value is a very long string that represents the geometry, the BREP geometry. And as I said, sometimes that brep string will come back none. Maybe, as I said, these rogue vertices do not have those brep strings. So if brep string, if it is not none, basically, let's make a topology out of that brep string. And I have in topologicpy an API call or method called by brep string. So topology.by brep string, I give it the brep string, and it gives me a topology, right? I want to make sure that this operation has succeeded, because if it doesn't succeed, I will get none here for the topology. So if topology.isInstance topology, meaning that this topology, lowercase t now, that I received from topology.bybrepstring is an instance of the class topology, as you can see here written, meaning topology is obviously the superclass of everything. Meaning, is it a geometry actually? Is it a cell complex or a cell or a shell or a face or a wire or even a single vertex or an edge? But at least it is a topology. If it is, that means it can take a dictionary. Therefore, I take the dictionary that I got from the vertex, D, and I store it now inside this newly created topology. Great, so that hopefully will work. And then I add this topology to the list of topologies that I will display later on. Now, if there is no topology, if it is not an instance of topology or something went wrong, maybe it is a bad topology, like a bad geometry, something happened that did not work. If that did not work, I add the vertex to the rogue vertices. That's all I do. I mark it as something that needs to be deleted later on. Now, that happens if the topology was not being created. But what if there was no brep string from the beginning? If there is no brep string from the beginning, else also add that vertex to the rogue vertices. So these are the two conditions that result in V being added to the rogue vertices list. Either the topology was not being created, could not be created, or from the start there was no brep string. I hope this is clear. So now I have a list of rogue vertices and I have a list of topologies by running through every vertex in this graph, by looping through all of this. So next I remove the rogue vertices from the graph. So I say for rogue vertex in rogue vertices, graph1 is equal to graph.remove vertex graph1 rogue vertex. So I just loop through every vertex and I remove it one by one from graph1, saving the result in the same variable. So at the end of this loop, I should have a clean graph1 that has only vertices that have geometry associated with them, and all the rogue vertices are removed. Graph.remove vertex removes the vertex and removes any edges that are connected to that vertex. So it cleans it up nicely for you. Right. Now, because of the display later on, I'm going to display these nodes using their IFC name. So I decided to add another IFC name, kind of like a fake IFC name, to the graph, to graph1, to the whole graph. So I created a new dictionary, D dictionary by key value. The key is called IFC name, like the nodes, and you'll see them later on. And I decided to call it just graph, like this. So a graph, like a topology, can have a dictionary as well. This is not the dictionaries of the nodes. This is another dictionary, separate dictionary for the whole graph structure, for the whole graph object. And therefore, I set graph1 to be, to set a dictionary to graph1, excuse me. And I print done. So let's go ahead and run this. This will take a little bit of time. Obviously, it's reading a large IFC file with a lot of geometry in it, but let's just wait for it. And I will pause the recording for just a second. Here we go. It took 1 minute and 46 seconds. So now what are we going to do next? So now we have graph1 cleaned up, and we have the topologies and everything else. So what I decided to do here is to exercise one of the space syntax metrics that we have, which is called closeness centrality. Closeness centrality measures how close a vertex is, a node in the graph is, to all the other nodes. You can read about it if you are not familiar with closeness centrality measures. So when you run graph.closeness centrality, it will measure this metric called closeness centrality for every node, and it will save that score for the node in its dictionary automatically for you, okay? As well as return it as a list. So let's go ahead and run this. So what I do here is that once it is saved in the dictionary, I'm basically getting the dictionary of that vertex. I'm looping through the vertices. I'm getting the value that has been stored, which is called closeness centrality. If you look at the API documentation, it will say that the default name of the key is closeness underscore centrality. And I'm changing the value because it's a little bit low to multiply it by 20 and then add 4 to it. This will become really a pixel size at the end. So I'm just changing the size of the pixels, the size of the nodes, excuse me, based on their centrality so that vertices that are more central appear larger. And then I set it back to the vertex. I take that dictionary and copy it over and overwrite the old dictionary with it. So I do that for every vertex and vertices. So let's go ahead and run this. Okay, it ran. So now it's time to actually see something visual. So let's go ahead and do topology.show. I'm showing graph 1. I'm saying that and this is new, by the way, in the newer version of topologicpy. I'm saying that the name key is IFC name. This will be like the legend name. Sagita or Sagita, I don't know how you spell this. Basically, I consider it the SAG. The SAG is basically creating instead of a straight line between the nodes, I'm creating an arc. And this arc is basically 5% of the length of the edge. So when you say absolute is false, rather than move it by 0.05 at its apex, it is moved by 0.05 of the total length of the edge. And it creates a really nice curved edges for your graph. I'm setting the face opacity to 0.1. So you'll notice that even though it is topology.show, I'm showing a graph 1. The nice thing about topology.show is that it can show topologies as well as graphs. Graphs are considered also topologies. And it has some input parameters that are specific for graphs, like Sagita here, and the absolute. And it has other things that are more suitable for or more appropriate for the topologies itself that have faces, edges, faces, and vertices. So you'll notice here that I'm telling it to use as a vertex size key to look at the closeness centrality, meaning that for every vertex that's being drawn, it will consult its dictionary, it will find this key that's called closeness centrality, it will get the value of that key and use that to change the size of that vertex. Same thing for vertex label key. Again, it will go to every vertex, find the dictionary of that vertex, find the key in that dictionary that's called IFC underscore name, and pull out that value and use it to actually label that vertex. So you're going to see actual IFC names. And then the color coding, the actual colors, are based on groupings. And the grouping has an input value called vertex group key. Again, it will go to every vertex, go to the dictionary, pull up IFC type, and use that to come up with vertex colors. And how does it know about the vertex group? I'm telling it here are the groups that I'm interested in. I decided to add something called unknown so that IFC space is colored slightly differently. But basically, it will find the group as an index in the list here. So is it the first one, the second one, the third one, and use that number to come up with a color based on a spectrum of colors, and you can change the color scale as well. And then there are other things like showing a legend on the side. I'm saying false here. I'm setting the background color to be white, and I'm setting the overall size of the figure to be 1024 by 900 pixels. So let's go ahead and run this one. And here is the graph of that building. Now, you will notice if you are carefully looking at this that it has separate graphs. They are disconnected. So there are these skylight graphs here, and they are separated. There is a set of nodes up on top for the roof. Then the middle part looks all connected, but if you are really careful, you might find some um, nodes, like I'm putting my cursor around them, like here and here, that are disconnected. These are isolated. And then there is an isolated subgraph at the bottom made out of all these green nodes, as you can see here. Now, this might not mean much to you, but let's go ahead and draw it with the building itself. So let's go ahead and change this so that we are drawing also the topologies. So you can just add it with a comma here, and it will draw the topologies and graph one. It will take a little bit longer, of course. And here we are. So now this is the full three-dimensional geometry. Separated, this is not a cell complex. This is each vertex has its own B-rep. But you can now see the correspondence between what the IFC file is seeing as a graph and what the building looks like. But as I said, the IFC graph is not fully connected in this case, in this example. There are breaks in the connectivity. If I had built a cell complex out of this set of solids, I will get hopefully a fully connected graph. So there is a difference between what an IFC graph is, which what you see here on the screen, and what a cell complex graph or a dual graph of the cell complex would look like. All right, so we have this now. So let's see what we are going to be doing next. The next thing, and really we don't need any of these because we have them up on top, but it doesn't hurt to have them. The next thing is to exercise a new method called connected components. Think of connected components as islands. I actually was about to call it graph.islands because it is more intuitive, but the purist in me, wanted to call it something that the graph theory people would recognize. And in graph theory, they don't call it islands. Nobody calls them islands. They call them connected components. So I decided to keep it as connected components. So components equals graph.connected components graph one will simply give you back a list of graphs where each graph is a independent kind of component, as you can see here. So you imagine if we remove the topologies from here and just redraw this graph. So it will give, for example, the top graph here, this one, this set of nodes by itself, these four nodes by themselves, these four nodes. You'll notice there's even like a little node here by itself. There are a lot of individual nodes that are floating, that are not connected. And of course, the big one in the middle, that's all connected, it looks like. And then there is one at the bottom. The connected components method returns the components in a sorted list from the graphs that have the highest number of vertices to the lowest. Okay, so that because probably the ones with the highest number of vertices are of more interest to you. So now we get them and we then show them. So now I'm showing the first four of them. So let me change this and show only the very first component, which with the highest number of vertices. So let's go ahead and run this. Here we are. So as you can see, this is all connected, but it doesn't have the top part and the lower part. All the dictionaries are in there, so I'm still getting the same color coding. So let's go ahead and get the second highest component. So we'll get components 1. I'll run it one more time. As you can see, This is the bottom one that has the next highest number of components. As you can see it here. This is this one at the bottom. So this has 1, 2, 3, 4, 5, 6, 7. This one here will be probably the next one. 1, 2, 3, 4, 5. So let's get the next one, which is components 2. And let's throw this. And as you can see, it's the one on the top. So if I want to draw them all together, I'll simply say draw from 0 to 3. And you get 3 subgraphs thrown together. Or if you want to draw them all together, just take out the square brackets and draw them all together. And here is the full graph again, drawn all together. I hope you enjoyed this tutorial. Please go to GitHub and download this Python Jupyter notebook and try it out, and let me know if you have any questions. Thanks again.